All right, so we're going to begin this lesson, Unit 10. I'll label that. And I'm going to label it with the title of what this lesson is really about, Gibbs free energy. And you did watch the Khan Academy video, hopefully, and you took the notes off of the video and also from the notes in Khan Academy, but I'm going to recap everything here. So Gibbs free energy is entropy and enthalpy, the relationship between the two. Okay, so entropy, we have from last week found out that this is disorder, which is delta S. And then we have enthalpy, which is from Unit 9, which is our delta H. So maybe I'll just put down Unit 9, just a reminder of where we really focused on enthalpy, that heat. And I will jump in and write down the equation since we had a little jump start from Khan Academy. Delta G is Gibbs free energy. It is enthalpy minus temperature times entropy. So the value of entropy and then the calculation of delta H and calculation of delta S. Well, just as a gentle reminder, you guys had some practice last week on calculating delta S through your delta S values. Unit 9 focused on your known values of delta H, and you were able to calculate delta H with your delta H values, your enthalpy values. So let me just put that down. So we have it in our notes again, delta H. You want to use delta H values. It is the sum of your products minus the sum of your reactants. I'll just put a capital R. To solve for delta S, you're using delta S values, but it is also the same equation. So your sum of all the products minus the sum of all your reactants. So it becomes a big math problem, as you may have seen from the notes. So once I have that calculation, I can plug in that value here. Once I have my delta S, I can plug it in with this value here. And then you see that both of the reactions, or both delta H and delta S, also depends on what the temperature is. Okay, so it is temperature dependent as well. And this is the relationship, otherwise known as Gibbs free energy, is the relationship between enthalpy and entropy. Okay, relationship between enthalpy and enthalpy. Let's write that down. So Gibbs free energy, put a little arrow down here. This is the relationship between, well, let's say, and doesn't make a difference in how we say it, but entropy and enthalpy. Okay. Now, one more thing that we learned from last week is that temperature needs to be converted into something called Kelvin, which we've heard before. We've used that terminology before. That is the International System of Measurement for temperature. So temperature, let's make a note. I'll put a little asterisk of the importance here. Temperature must be in Kelvin. So the symbol of Kelvin is not degrees like it is for degrees Celsius or degrees Fahrenheit. It is just a capital K for Kelvin. And to simplify it, or to convert it rather, not to simplify, you can convert it by having your Celsius, so your degrees Celsius, plus your 273 value. So when you add 273 to the value of Celsius, degrees Celsius, you get your answer in Kelvin. So then in order to put that value in there, you need to make sure that it is always in Kelvin. So let's just put a whole bunch of asterisks there. Temperature must be in Kelvin. And we're going to get into the unit of gas laws, and that is the same thing. Gas laws need to be converted into the unit of Kelvin. All right. Little background, there is this Gibbs, this free energy. The relationship between them was discovered by a physicist named Mr. Gibbs, Dr. Gibbs, Joshua Gibbs. back in the late 1800s, early 1900s. And then there's some facts I want to add to it. So I'm going to add a little bit of notes here, because what does having that relationship mean? Well, the relationship basically says if the forward reaction will occur spontaneously. Will it occur without any outside source rather? Or will it not? Will it be non-spontaneous? So let's see. If I have a delta G value after all my calculations, if I have a delta G value that is less than zero, meaning I have a negative delta G value, then the reaction excuse me, is considered spontaneous. All right, so if the delta G value is less than zero, a negative value, the reaction is considered spontaneous. This is favorable. Let's just write that in there. If your delta G value is greater than zero, meaning it's a positive, the reaction is not spontaneous. And then there's scenarios that delta G may equal to zero. And if the delta G is actually equal to zero, the reaction is considered at equilibrium. We have an entire unit devoted to going over what this equilibrium reaction does and shifting equilibriums and such. So there is an entire unit on this, but this is what the delta G values represent. So there are scenarios that, well, what is favorable? Like how, even if I didn't calculate, could I figure out if something is favorable for a reaction to occur or unfavorable, I guess, if by saying non-spontaneous, the forward reaction? There is. Okay, so I'm going to go further and make like a little chart here for you. So this is a nice go-to chart. And I kind of put everything into place. Let me bring this down a little bit. There we go. So if we have an exothermic reaction, let's talk about let's make a little chart. I'm going to put enthalpy change, which the symbol is delta H, unit 9, and then entropy change, which is the introduction of what we learned last week, delta S. And let's add to that. Is it spontaneous reaction? Question mark. So I'll make a little table here of all the scenarios possible for all the reactions. Again, if you were able to identify if something would occur spontaneously or not. Let's make little boxes here to include that. All right, well, let's look at the scenarios possible. If I had an exothermic, so exothermic reaction, that means your delta H is less than zero, which was a negative value heat. That told us that the heat was leaving the system. That was our unit 9, guys. There's a scenario you could have exothermic reaction, and let's say you increased your delta S was increasing. You had a positive delta S, you're increasing. So you calculate delta S, it was positive. You calculated your delta H and it was negative. So you have an exothermic reaction with lots of disorder. So lots of abilities for those reactions to bump. This would always produce a spontaneous reaction. So if you were to calculate it and actually put in values to determine your Gibbs free energy, your Gibbs free energy would come out to a negative value. Okay, so these two in Gibbs free energy equation would always occur. That's the most favorable, the most ideal situation. All right, so we could have an exothermic reaction again. Let's just rewrite this for the sake of my notes. delta H is less than 0, we have a negative value. Remember, not a small number, but that's a negative value indicating it's exothermic. But now instead of increasing, let's say you're actually decreasing. You're becoming more orderly. Your delta S is negative. So you're less disorder, or in other words, you're orderly. Well, you could still occur. This exothermic reaction makes it quite favorable of giving off energy. However, this is not a favorable situation, but the reaction can occur. So say yes and no, right? Yes and no. It really is depending on the temperature. Only if the temperature is low enough. Because as you plug it back into, let's go all the way up here, as you plug it back into, if it's low enough, we will still get a negative delta G, and we'll have it as a spontaneous reaction. Okay, so there is a scenario that could make it spontaneous only if yes, only if the temperature is low enough. All right, well then you can have an endothermic reaction. Not favorable. However, it happens. We have an endothermic reaction. It could still occur. Okay, so if you have an endothermic, let's remember what the delta H value would look like. That means you have a positive delta H value. Well, if you have an endothermic reaction, although not favorable, right, this is producing something that feels cold, and let's say you have an increase of your delta S, so you have high disorder, which is quite favorable. This scenario could occur, so yes, well, let's put yes and no, because not necessarily always occurring, but yes, if the temperature is high enough. So what that means is that your value, bring it all the way up here, that is, this number is high enough, this value is going to produce a negative delta G, and that is going to say it's spontaneous. But again, if the temperature isn't high enough, it will not. So it comes down to the math behind it. And then the last scenario, you would have an endothermic reaction. And for the sake of our table here, let's continue with repeating that that's a positive delta H. But let's see the scenario if you're decreasing. So we have an unfavorable situation, right? Not favorable. And we also have an unfavorable situation for your delta S. Let's put that in there like that. So you have a negative and a positive endothermic, positive delta H. This situation is not going to happen. It's not going to be spontaneous. Okay, so you cannot produce a spontaneous reaction if you have very organized, I guess. So you have a low entropy and you have endothermic reactions. This reaction will not be spontaneous. You need to include some energy. Something has to happen, but more than likely that reaction will not occur. All right, so this is the table to have in your notes as you're going through today's questions. I'm going to now stop my recording